Good afternoon, dear colleagues. Greetings and welcome to the next part of our course in research methods. Today we will be focusing on the most important, probably, part of our course, research designs. And over the next couple of lectures, we will discuss what is experimentation, how does it work, what kind of research designs do we have available to us in social sciences, and what are the differences between different experimental design in terms of the conclusions that we can make and in terms of the difficulties that we can encounter. Today, we will begin with the cornerstone of all social science research, experimentation. The paradigm of experiments is very well developed in our area because sometimes it's very difficult to ensure that we are really able to make the causal conclusions that we are looking for. So we will begin by addressing the issue, why at all do we need those experiments? What kind of purpose do they serve? And why can we not actually get by without them in our science? And the very simple answer is because we want to make causal inference, because we want to know the causal laws that govern nature, and we are not interested in simple statistical associations, but we are interested in proving that actually behind this association there is a cause and effect relationship. And one very important principle that potentially, if I were more sadistic, I would ask you to write on the blackboard 100 times, like Bart Simpson is doing here, is that correlation does not equal causation. It is not enough to observe an association between two variables to infer that there is some causal link behind them. Now, this has been known for ages. Aristotle, Galileo, and many others distinguished different type of causes and observed that when two things coincide, it does not necessarily mean that they are connected. And online you can find a lot of different data sets where you can see bunches of variables that seem to be very closely connected, but there is no causal relationship whatsoever. For example, here you can see the association between the share of Internet Explorer browser and murder rate in the United States. And of course, if you're a social scientist, you have a trained mind which is able to develop all kinds of interpretations, and you can say, oh, maybe Internet Explorer was such an awful browser that people got angry when it froze and they started killing each other all around. But probably the explanation is more simple. Perhaps it is just a spurious correlation, and there is no causal association behind these two variables whatsoever. What kind of conditions should we meet in order to be able to make a causal inference? Those conditions were described by many scientists. Aristotle, Galileo, David Hume contributed a lot to this. But in their final form, they were formulated by this a bit serious-looking man, John Stuart Mill, in the 19th century. And he argued that in order to prove a causal relationship between two variables, three conditions must be met. The cause must precede the effect in time. The cause should be statistically related to the effect. When one arises, the other one should also arise. And the third condition is extremely important. We should not be able to find any plausible alternative explanation for the effect other than the cause. Now imagine that you see a wind blowing and the trees are starting to shake, and you say, okay, maybe the trees are shaking because the wind is blowing. In order to make this conclusion, you must first observe that the wind starts to blow and then the tree starts shaking. That whenever the wind blows, the trees shake, and whenever the wind doesn't blow, the trees don't shake. And the third condition, there should be no plausible alternative explanation for trees shaking other than the wind. For example, there is no earthquake around, a neighbor boy does not shake the tree, etc. And all these three conditions must be met in order to make our causal inference. Now, the third condition is very important, but it is very difficult to meet in actual research. Let's take, for example, this longitudinal study, which I'm particularly fond of, being a very strong coffee consumer for many years. And this longitudinal study has found that actually people who drink a lot of coffee, they are less likely to die over the next 12 or 13 years. And these researchers used a very large sample of people, something like 10 or 12,000 people. It was a population study, and they asked people how much coffee do you consume on a regular basis every day. And then over the next 12, 13 years, they monitored the conditions of these people, their health, whether they would be likely or not likely to die. So basically, they monitored the objective outcomes related to their health. And they discovered that people who drink a lot of coffee, 2, 3, 4, 5, or 6 cups, their risk of death over the next decade is about 10 to 15% less than for people who don't drink any coffee. And this is a longitudinal study. So there is the precedence, first coffee, then death or no death. And there is a statistical association, which is proven by statistical analysis. Now, the question is, can we actually infer that it is coffee that prevents early death? And you can put this video on pause and think of the possible alternative explanations. Why do people who drink a lot of coffee are less likely to die? Now, if you have reflected a little bit on this simple exercise, of course, there are a lot of alternative explanations that we can propose. Maybe people who drink more coffee are less anxious about their health. Maybe they know they are less at risk for heart diseases and they are not afraid to drink coffee. Or another potential alternative explanation is the level of income. Maybe people who can afford to drink a lot of coffee, maybe they can also afford to go to good doctors and spend more on healthcare, or maybe they exercise because they can pay for a gym membership, etc. So there are many possible alternative explanations that can potentially explain the causal reasons behind this association. And this is why in medicine it very often happens that first researchers say, oh, eating eggs is bad for you because it increases your cholesterol. And then after a while, after a decade or two, they say, oops, we were wrong. It is not actually eating eggs, but it is something else that causes cholesterol. And people who eat eggs are also likely to have this thing together. So this is just one example of a longitudinal study which is not sufficient to infer causality, even though it is much more persuasive as evidence compared to a cross-sectional study where you don't have even this difference in time between the cause and outcomes. So the only study design that allows us to meet all three conditions of causality is experiment. In an experiment, the cause precedes the effect in time. And we manipulate this cause. We create these conditions, the presence or absence of this cause, to make sure whether the effect comes up or not. Statistical association. Of course, when we manipulate, we also try to check statistically that the differences in the effects that we observe are related to the presence or absence of our cause, and it is not just an accidental association. And most importantly, we are trying to create conditions in which we try to reduce or eliminate the plausible alternative explanations, the extraneous variables that can coincide with our cause and play a role in creating our effect. That's why in an experimental design, we have the strongest grounds for causal inference whatsoever.